Okay, so good evening, everyone. Let's start today's class. So there will be another extra session on, I think, 18th. Yeah. So you'll get an reminder email, but yeah. So and this will be around same time. Let's say 6 to 8. Okay. So the about timing, I have to actually check. I think this is not same time. So let me check just once. Okay, so about timing, you'll get to know from the email actually. This is not confirmed. It can be from 10 to 12 or the usual time 6 to 8. Okay, so before going to the specific questions, let's start some by solving some of the derivations which was not done, although these are straightforward in with 8 lectures, let's say, mostly commutation relation and other definitions. So to understand that fractional quantum Hall effect, we went to the symmetric gauge, where the magnetic field, or the rather the magnetic vector potential, is represented by some symmetric combination of x and y, and of course the magnetic field r cross b, which is half of minus by x cap plus bx y cap. Okay. And because of this explicit y and x, this breaks translational symmetry in both the direction. Both x and y direction. And the reason is simple. If we have simple Hamiltonian, and if px doesn't commute with Hamiltonian, then we say the translational symmetry along x direction is broken. And similarly, if Hamiltonian doesn't commute with py, then we say the translational symmetry along the y direction is broken, because the momentum operators, or px and py, are basically the generators of translation along their respective x or y direction. And for us, for since we are dealing with free electrons, Hamiltonian is simply px square plus py square by 2m. So this is the in presence of no magnetic field. And then we of course have uh, px minus uh, rather in general P plus EA square by 2m in presence of finite magnetic field. Okay, okay, so we define generalized momentum tau, or let's say pi, as P plus EA, which includes the effect of magnetic field. And sorry, we cannot actually open the exam form. That is NPTEL's. I mean, they have the authority to do it. We do not have any. Uh, so we only do tutorial sessions. We cannot see even the exam form, or let's say other things also, assignments and other things. So we have to email NPTEL for that. Okay. So define raising and lowering operator A as root over pi HEB pi x. So this pi is just 3.14, the value of pi, let's say, and this pi is operator, which is momentum, generalized momentum. It includes the conventional momentum and plus the effect of magnetic field via vector potential. And then A dagger, which is the raising operator, pi x plus I p I pi y. Now if we do commutation of this, so this is actually kind of similar to what we have done in uh, simple harmonic motion, or let's say, yeah, simple harmonic motion in quantum mechanics, harmonic oscillator. So this can be written as A dagger minus A dagger A, which is, just use these expressions. So we'll have pi by HEB as a constant, and then pi x minus I pi y, uh, pi x plus I pi y minus pi x plus I pi y, pi x minus I pi y. Right? And we just need to multiply things with correct orders. Pi x square plus I pi x pi y minus I pi y pi x plus pi y square minus pi x square minus I pi y pi x, and then plus I pi x pi y minus pi y square. So we are left with, let's say, so these things cancels out. Uh, this one and this one, and we have two of them. So 2 pi h bar, sorry, HEB I pi x pi y minus I pi y pi x. So this will be I by EB. So you can write h bar EB. H bar is simply sorry, h bar is simply h by 2 pi, and then we have just the commutator of pi x and pi y. Now let's derive what is the commutator of pi x and pi y. So pi x pi y is simply px plus e a y, py plus e a, sorry, this will be ax and this is a y. So px plus we have ax equal to, so from this thing, this expression, we have ax equal to minus by by 2 and ay equal to uh, bx by 2. So we have minus by 2. No, so we cannot reopen. Okay, so we do not have the authority to reopen the exam. So we are just the tutorial session. We are in charge of only conducting the tutorial sessions, and we do not have access to the portal or any other thing actually. Okay, so this you have to mail to the NPTEL authority. We're just for the tutorial sessions actually. We do not see your assignments as well as lectures and so on. So altogether do not have any access actually. Sorry. No, you just mail them that you missed the registration process, and most likely they will reopen for you if there are enough time. I think 18th is the last date for the assignments, and 18th kind of lectures and other things also finishes. So before that you have to mail, and if they reopen then you will be able to register.
Sir, how can I register for examination, sir?
No, that's what I am telling, that we are not so we are not the authority to do it. Okay, we do not have access to their portal and so on. So you have to mail to the NPTEL.
Acha, or sir, please, if you give a email address.
Email address, okay, let me search. There are two email address. No, so one main, I think,
Ji.
online courses.
Online courses.
So the email address from which you get regular email for the tutorial sessions or
हाँ
video
हाँ.
lectures have been uploaded, etc.
अच्छा, वो उसी पे हो जाएगा.
Right, right. Huh.
Okay, okay, sir. I will mail today.
Mm-hmm.
Okay, thank you.
Yeah. Okay, so you have px and then minus eby by 2, and then py plus ebx by 2. Now if you simply write each part separately, then we'll have ebx by 2 and then minus eby by 2 py and then minus again eby by 2 ebx by 2 and so on. So this is 0 because px and py already commutes, and this part will have some contribution which will be minus I h bar, because we know that the commutation of xi, let's say, or yeah, xi, or in general I can also write ri pi is I h bar. Ri can be so ri, when r1, let's say, we can have x, r2 y, and r3 equal to z, let's say, in general. And then this is already in order, this term. So eb by 2 I h bar y py commutator, and this is also 0. X and y also commutes with each other. So we'll have minus I h b. So in general, we can also write this as so pi I pi j equal to minus e. Sorry, I missed one. Uh, just a second. We had iota here. So okay, so okay, it is fine. So I was deriving this only. Fine. So we'll not have any I. So we'll have any I, E, and H bar. Yeah, it's fine. So in general, we can write that it will be I, E, H bar, and B, K, epsilon I, J, K. And this will be plus then. Or no, it will be minus for general case. Minus. So epsilon ijk is plus 1 when ijk are clockwise, and it is minus 1 when they are anti-clockwise, and 0 if any of the two indices ijk are equal. So let's say I equal to j, or j equal to k, or I equal to k. Anything can happen, and this ijk corresponds to x, y, z Cartesian coordinates. So then, so this is the commutator relation of pi x and pi y. So then commutator of A and A dagger will be we had I by h bar E b, and now we have this term minus I E h bar b. So all of those things cancels out, and we will have minus I square, which is plus 1. This is what we also have seen in simple harmonic oscillator in quantum mechanics. Okay, so uh, so the operator pi are not really canonical, because for canon to be canonical, we need the operator to be operators to be 0, but that's not the case, right? So pi operators. So let me write more clearly. Pi operators are not canonical since they do not commute. So is the A and A diagrams. Okay. Now there is another form we can introduce pi tilde. Pi tilde, these are vectors by the way. So pi minus EA, right? So if we introduce that, then this will be canonical because even we don't need to solve this. So if we derive or explicitly evaluate pi x and pi x tilde and pi y tilde commutator of this will be 0. We can simply see this from pi is p plus ea and minus ea, right? So effectively it becomes p are the momentum in, so in absence of magnetic field, let's say. So then px and py commutes we already know from quantum mechanics. So effectively will have pi x tilde and pi y tilde will commute with each other. But these are pi x tilde and pi y tilde. These were introduced to sort of uh, define another set of operators. We defined already A and A dagger, which is equivalent to the raising and lowering operator in the harmonic oscillator of quantum mechanics. And this using this pi tilde, we will define another set of operators, almost similar form, just the normalization factors is going to be different. So this is B, which is defined as root over 2e h bar B and pi x tilde plus I pi y tilde and B dagger cap, which is okay. Now we can say that B and B dagger commutation relation is also going to give 1, similar to what A and A dagger is. So we had A dagger equal to 1. So let's evaluate what is B and B dagger. So this means we'll have 2e h bar B and then we have pi x plus I pi y all are tilde commutated with pi x minus I pi y. So we'll have pi x tilde plus, sorry, this should not be third bracket, otherwise it may create confusion. Pi x, okay, so let me do pi x tilde plus I pi y tilde, and then pi x tilde minus I pi y tilde, and the opposite. So this will be pi x tilde squared minus I pi x tilde pi y tilde plus I pi y tilde pi x tilde plus pi y tilde square minus pi x tilde square, and then minus I pi x tilde pi y tilde, and then plus I pi y tilde pi x tilde minus pi y tilde square, right? Again, similar to the previous case, we will just have, so these terms are going to cancel, and we'll have 2 2e h bar b, and let's say minus I pi x tilde pi y tilde, and then plus I pi y tilde pi x tilde. So minus I e h bar b, and then pi y tilde. Okay. Now what we have seen is that pi x tilde and pi y tilde, they basically commutes here. So from this we can also say this is 0. Okay, so this is not equal to 1, but this is 0. Okay. So any point, so in the lecture notes, what I am saying is that pi x tilde and pi y tilde are defined as what we have defined, but it says that just a second. Yeah, it says that B and B dagger gives also 1. I mean, the commutator of B and B dagger. But if it is defined in pi x tilde, it should actually give 0. Just because pi x tilde and pi y tilde commutes with each other. So I'll just check once. I think this calculation is already correct. I mean, there is no issue. It is just as same as the A and A dagger commutator, but involving tilde operators. And tilde operators are defined in such a way that we are effectively excluding the magnetic field effect, let's say, because pi was P plus EA, right? So somewhere we defined, yeah, pi was P plus EA, and then if we add another negative of minus EA, and effectively it reduces to the conventional momentum. So I'll check this, and in the next class it will be clarified. Okay, so one question one of one of you have just emailed me. David, okay. Let's solve few more questions and then we'll move to specific questions. So one question was question one, let's say. I'm just writing that question sent by Sonam Khan and then I'll answer. so that everyone can follow the question and answer accordingly. Uh, it's fine. So this was the question. David Tong's lecture note while calculating the TKNN invariant, which sometimes we also call Chern number, some specific cases. How did tensor product of single particle wave functions is found? Okay, it's found from the many particle or multi-particle wave functions. Okay, so in the David Tong's lecture notes, if I just uh, write down the TKNN invariant formula, or let's say Chern number. It was actually written as something like fxy. And then chart number was minus 1 by 2 pi close integral b2k fxy. So these are written in terms of, let's say, single particle wave function. U is wave function or wave vector, let's say, and their derivative is associated with some sorry, some field kind of thing, which we in anomalous Hall conductivity, or in this construct we call it Berry curvature. Fxy is nothing but Berry curvature. Now this is the single particle form of it, but before that the Hall conductivity from the Kubo formula was found with a general let's say form, which was again kind of Berry curvature type of thing. Okay? Where so from the Kubo formula we found that sigma xy Hall conductivity can be written as I h bar, and then sorry, so let's say n not equal to m, jy is the current operator along y direction, n, and n and m here are multi-particle wave function or many particle wave function, jx minus m. Okay, so now this can also be written as similar to the Berry curvature form. Okay, so we wrote it, we can write it in kind of Berry curvature form by assuming that perturbating Hamiltonian is in our case is definitely the magnetic field. I can go to x and y, and gi is the current operator along respective direction, and phi I is the flux, and then associated length scale. So assuming this as the I mean kind of perturbation, and writing things in terms of, let's say, this delta H, and where it is associated with the j, phi, and li, we can actually write this term. So the details of the derivation is given in Davidson itself. So we can write in terms of, let's say, del phi y, and then m del n, sorry, del m itself, phi x and phi y are the flux components, minus del phi x, and then m del phi, sorry, del m it will be. Okay, so these are the multi-particle wave functions m and n so on, and you see similar form is also there, right? Now the point is not really directly we are coming from multi-particle or many particle wave functions to a single particle wave function. This was just an analogy that when we derive the Hall conductivity expression from the Kubo formula, we get a similar kind of form, which is in other ways also we can derive or we can arrive at to be Berry curvature. I mean, it has the same form, and by extensive calculation, we can also show that it is equivalent to Tkn invariant, which is some topological invariant, let's say, associated with the quantum Hall effect, or let's say topology of the system. Okay, so it is not really coming from the many particle to single particle wave picture. It is just an analogy that this similar kind of form comes. In fact, this Kubo formula in the sigma xy, we do not have any integration, right? But when you do in the k space, the simplest or most elegant example will be the anomalous Hall effect driven by Berry curvature. You automatically get integration, k space integration of it. Okay, and this will reflect in chart number. So it's kind of analogy. It is not really coming from one to another. The concept here remains that we average over all the flux quanta, or the flux, we average over all the flux quanta. That is kind of equivalent to the integration. But in case space, when we derive anomalous Hall effect expression, the the integration automatically comes as a Brillouin-John integration. Okay, so there are next few questions that I will answer. There is another question. Can we explain solution of assignment 7 question? So assignment 7 question 2 was okay. So this is explain how massless Dirac fermions arise at the interface of HGT CDT superlative structure. So for this, we need to have some critical length, or let's say critical depth of the quantum well formed at the interface of HGT and CDT structure. And so once you achieve at some critical length and do the band structure calculation, of course this is not a simple system like graphene where we can uh, formulate the analytical theory. Let's say that sp2, I mean there are two s orbital and then three pz orbital. So there is sp2 hybridization and then one unhybridized pz orbital, and from there we derive the tight bending Hamiltonian of graphene, let's say, including only pz orbitals. This is not possible here because first of all this is already a interface, so all of those things needs to be considered, and this is usually done numerically. One of the method is density functional theory and so on. So from that we just need to tune the, I mean, quantum hole width, let's say, and then see how the band structure evolves with density and then uh, width and so on. Okay, and the important point is key, you just need to write about those processes. So we cannot have any, or we do not have any simple Hamiltonian where you will kind of uh, extrapolate to Dirac fermions, let's say. Or similarly, what we did in terms of, let's say, graphene, we had some tight binding Hamiltonian, TB, TB tight binding Hamiltonian, and then around some point, high symmetry points, which were K and K prime, which we call Dirac points. If we expanded that Hamiltonian, or our sorry, so our Hamiltonian was simply like 0 Fk, F star K, and 0, and then around Dirac point K, which was, we can think of like, uh, it depends on how we choose the coordinate system, but if we expand f of k, let's say around k, kd, let's say, then we simply got linear in k momentum, right? So this is not possible here, we need to take into account other effect, but from the band structure it will be kind of clear that at some critical length and density we will find something like this. Okay, it's kind of linear or massless Dirac fermions, which is represented by h bar vfk. Okay, so for this question you just need to answer that at which I mean critical dense sorry critical depth and so on, how this emerges. I mean, the band structure evolves and eventually it becomes kind of linear around some high symmetry point, gamma, let's say. Okay. The next question was, while calculating Kramer's degeneracy, how does I sigma y acting on u k sigma gives u of minus k bar sigma? Okay, so this was, so, so I sigma y and kappa. So this is the time reversal operator. Okay, and what really time reversal operator does is that it reverses the motion, right? That's what the I mean the rule of time reversal operator, let's say. Now the point is, so you have some wave function u, let's say, is a function of k and sigma. K is the block momentum, and then sigma is the spin of associated with that wave function. Now what will happen under tau? Under tau, k goes to k prime, sorry, minus k, k goes to minus k. We can think of like, since under time reversal the motion reverses, or that's how we define time reversal operator. So then k is the momentum, so the velocity also gets reversed, so is the momentum. And spin changes its sign, so under t sigma also goes to minus sigma, where sigma is spin, which is sometimes also denoted by sigma bar. Sigma with bar is nothing but minus sigma, just the opposite spin. If it was up, it goes to down. Okay, this we can understand from the nature of the spin actually. So spin represents some intrinsic angular momentum associated with the electrons actually. Now angular momentum is something that also changes sign under time reversal, because angular momentum also represents some kind of motion, right? Rotational motion. So if we have, let's say, uh, this circular motion along this way, and it's kind of outward from this page of a drawing, let's say, so this is outward, let's say. Now if we have some circular motion which is in the opposite direction, then it will be inward, right? So this is, let's say, minus L, and this was plus L. So this is the normal conventional angular momentum if a particle rotates around some circular path, let's say. Now spin are also associated with some intrinsic angular momentum, which should not be, I mean, contrasted or let's say understood with any classical system. So spin has some intrinsic spin actually represents some intrinsic angular momentum for the electron. So essentially, since it is angular momentum, so it will also change sign under time reversal, similar to the uh, conventional angular momentum. Okay, and that's why under time reversal, u of k sigma goes to u of minus k and minus sigma. Sorry, sigma is not a vector. Okay. Hello. Any questions?
Good evening, sir.
Yes, yes.
Sir, I want to know, sir, as I am interested in
Sorry, your
some
voice is
research
not
in
clear.
this topic.
Your voice is not clear.
Good evening, sir.
Yes, yes. Huh?
Sir, I'm interested in this topological um, insulators and also while semi-metals.
Mm-hmm.
Sir, I want to know, in some literature I have gone through that they getting the band structure of the bulk. है ना? We can, by applying spin orbit coupling, then we can create a Chern number.
Mm-hmm.
So, is it possible, sir, as you were discussing that Chern insulators, we require two-dimensional electron gas or some graphene-like substance means in two dimension we need a substance to observe these topological features. So, is it possible, sir, to observe and to calculate the Chern number by using the band structure of the bulk?
Yeah, we definitely calculate Chern number using the band structure of the bulk actually. Yes, it is possible. Uh, okay,
Okay,
so
sir.
Chern number is not only related to the band structure but more intimately related to the wave functions of the states. Okay.
Yes, yes,
Of course,
yes,
wave
sir.
function affects the band structure, so you can say that band structure is also related. That's true.
Okay, sir. So, sir, suppose if I get any doubt regarding my research, may I have some help or guidance from your side if you provide any such means to further contact and discuss problem?
Yeah, not an issue. So you are doing PhD or MSc? Just
Yes,
to
sir.
clarify.
PhD, sir.
Okay, okay, not an issue. I do similar kind of
Okay, sir.
things, so you can email me at uh,
Could you provide your mail ID, sir, so we
yes,
can
yes.
further?
So I already
Okay.
sent some. Okay, so this is not really related to the topological insulator and a churn number, but three, four people used to join regularly, so I have their email address and I sent them some materials actually.
Okay, sir. So actually, I'm working also. That's why, sir, I face some problem to attend
Mhm.
this problem
No, it's
solving
okay.
session because the timing is not suitable, sir. Sometimes,
Mm-hmm.
that's why, sir.
No issue, no issue. So you can email me at this address. So
Okay, sir.
sunitd@itk.ac.in.
So, at the rate,
Right.
okay, sir. Thank you,
Yes, yes.
sir. I want one of my colleague. He want to appear in the exam, but he missed the examination. Means to fill the examination form. So, is it possible that for some time you may open that link to
No, so
apply for
these
exam?
these uh, these are not our kind of responsibility, and as well as we do not have authority to do it. So our
Okay.
only thing is that conduct tutorial session and just upload the videos and lectures. That's it. We do not have any permission for their portal and anything actually. For that, you need to email to
Okay,
that
okay,
the email address from which you get regular notification about the courses.
okay, sir. Sir, could you differentiate between wild semi-metal and topological insulator, sir?
Okay, this is a little bit unrelated, but yeah. So of course, so when you say, so I'll just go superficial, okay, not very deep.
Okay,
When you say wild semi-metal, the simplest way to think is that it's a 3D graphene. In graphene, we have this kind of band structure actually around high symmetry K point. K is the Dirac point, right? Uh,
yes,
Around the Dirac points. Of course, tight binding band structure is something different. It will be kind of like this, although this is very bad. So this is the graphene case. And then while semi-metal also around some high symmetry points we will also have linear band crossings. Okay, again, so this is a pure 2D materials and this is a 3D materials. One of the example, let's say, sorry, tantalum arsenide, so TAAS. And why do we call it semi-metal? Semi-metal, so we, if we have metal, then you will have some band overlapping, right? So this is, let's say, conduction band and this is, let's say, valence band, and there is some overlap, so that with smallest excitation of electric field, let's say, you just have electrical conduction. On the other hand, if I draw some simple insulator and I have, let's say, chemical potential or Fermi energy somewhere here, then these electrons in the valence band is not going to conduct electricity, I mean go to the conduction band and conduct electricity. So this is insulator. And another more rigorous way to understand this is that in the, let's say, in the metal we have finite density of state at all points. So this will have some density of states, finite, okay, increasing dose in this direction. And if you draw, if we have some parabolic bands, something like this of a, let's say, simple free energy type model, and sorry, if you draw the density of states along this, let's say, we have K, and this is along, let's say, DOS, right? Or in the energy space, it is better that we talk about energy space because this is the energy direction. So this is also energy direction and this is DOS direction. So you'll see that somewhere you will have some DOS, let's say, and this is also some DOS. I'm just not going by the, I mean, very accurate way, in a sense that if I have K square type dispersion, then for 3D the DOS looks like root epsilon, and for 2D it is independent of energy, and for 1D it goes as 1 by root over epsilon. So I'm not going all these details, but what I try to say is that in this gap region you will have zero density of states, so there is no states there so that electricity can conduct, right? So that's the simple insulator and metal. Now we call graphene and wild semi-metal because there is a vanishing density of states at some point. So what really happens is that this is, let's say, conduction band, this is valence band, they touch exactly at some point. And if you think about graphene, then the density of states, like, it goes to 0. So this is, let's say, 0 point, and it starts, okay, density of states. So these are increasing density of states, and somewhere here at exactly at the Dirac point it goes to 0. So that's why we call it semi-metal. Now of course it's a 3D version of graphene and there are many other features and so on. So the main difference is, while semi-metal, you think of a semi-metal, graphene-like semi-metal, which have linear band crossing around the low energy, somewhere where we will have Fermi energy, let's say. And topological insulators are something we will have some insulator. I mean, uh, you will have some insulating area. There are some finite band gap in the bulk. Okay, although their edges are non-trivial, topologically non-trivial. Aids can conduct. That's why we call it topological, and it have I mean, there are various types of topological insulator. It might be Z2 or simply charm insulator type of thing, where aids conduct, and because of that, we'll have some anomalous Hall effect and so on. Okay, so this is the simplest definition, but there are many other rigorous ways of it. There is, I think there is a review by Jahid Hassan and some other people, which they have did very fantastic review and detailed, I mean, understanding of it. So I can send you that paper to all of you. Okay, so that's the basic level. Okay, there are a lot of other details. So is it clear? Hello, am I audible? Okay, so I think Sanam is here. So
Yes, sir.
yeah.
Hello, sir.
Hmm.
Sorry for joining late.
No,
Actually,
it's okay. So,
actually,
hmm,
a few question I sent you.
hmm.
Actually, oh, you have already explained this thing.
No, so this part, assignment 7, question 2, this you cannot show so simply, in a sense that this band structure, we do not have Hamiltonian, right, for this HGT, CGT superlative structure, or
Okay.
sir discussed, I forgot actually.
This Dirac like Hamiltonian that he discussed like this D dot sigma. So
Oh, that's a general form, right? So all I meant
okay,
was, I mean, so how do you say that graphene have massless Dirac fermions, linear band crossing? You just have that uh, h of k Hamiltonian in tight binding, right? 0 f of k, let's say, and then f star of k, sorry, f star of k and
yes,
0. Now you
yes,
expand this f of k or f star of k around some high symmetry points, which is k Dirac, and you see that f of k to the lowest order, it has something like h bar vf k, some form proportional to k. Now you say that okay, this is linearly dispersive, which do not have any mass term, similar to the high energy physics Dirac equation, because high energy physics Dirac equation was something like beta and some term, let's say momentum, linear in momentum term, and then m0 c square. This term is already absent, right? And there was no k square and other things, k square and other terms to the lowest order in k. That's how you call it. It's a massless Dirac fermions. Now in HGT also, if we have this kind of Hamiltonian, let's say analytically, we can solve that at some high symmetry point. We just expand those functions and see what happens. Then we can definitely arrive at those expression. But what I think is that it's a numerically calculated band structure. As you increase or decrease the thickness, there are some critical thickness of this AGT, CDT quantum well, and around those critical thickness, you will have direct or linear band crossings, right? So I think the question do not want to answer, or it doesn't require explicit Hamiltonian and so on. I do not think this exists actually. I mean, this may exist, but that will be quite complicated. This is already a superlative structure.
okay,
So it just wants to know that how you can arrive at those Dirac fermions just by tuning those quantum well width, or let's say density. Those details will be there in the lecture itself. So yeah.
okay. So and one more question actually from the David Tong's lecture notes.
That also I explained a bit. Okay, so the crux of the story is it is not directly related. Okay, so they just derived some analogy. So we are not going. We are not going from the many body to one body, let's say wave functions. Okay, we are not going that in that direction.
Okay,
So what we did is that we had some Kubo formula driven, or from the Kubo formula we have some expression of sigma xy, which looks like a single particle when we write Berry curvature in terms of single particle, right? In fact, if you really see the tk and invariant a Chern number, let's say you will have some integration over k. Here you will not
yeah,
get any integration, and it is kind of, it says that we do flux average for that. It's just an analogy,
Yeah,
okay? We are not
so
going from the one to another. Yeah.
you are explaining this TKNN invariant derivation for this spatial torus, this
Mm-hmm.
thing.
Hmm.
Actually, my question was actually from this TKNN invariant in the this reciprocal, actually, where the Brillouin zone become actually this T2 torus.
Exactly, that is the point. Key, these are not directly kind of. This was just an analogy actually. There are a lot of other details. So, in chart number, you need to do k-space integration and so on. Here, there is no integration itself. You do flux averaging, right? And this Corbino geometry itself was kind of thought experiment kind of thing, right?
Okay. So, and one more question
Hmm.
actually,
Hmm.
like as we have seen, like while solving for this Laughlin, this pump actually.
Hmm.
Uh, so there, this wave function was considered to be like this e to the power minus mod z square divided by 4 lb square form.
Right,
So, which is actually coming if one considers this symmetric gauge.
right, huh? Huh.
So, the reason is actually they are like based on the geometry, one will choose this wave function there.
Mostly we do that actually just for our convenience. So
Okay.
if you really I mean, so Laughlin states and the explanation of fractional quantum Hall effect was not there until we considered that Coulomb interaction, right?
Yeah,
So
yeah,
so you can think of before that, whatever was before that, it was kind of general, right? In Landau gauge, you explain that I have k momentum which is independent of energy. Energy is independent of k, but wave function depends on the k. So there is some degeneracy. So there can be a lot of wave function which can have same energy, because energy just depends on the n, which is the index, Landau level index, let's say, and magnetic field. Else everything else was sort of constant. So that's the way to understand degeneracy in the Landau gauge. Now, if you come to the symmetric gauge, then you will understand that, of course, kind of there is angular momentum operator associated, and again, similarly, the energy is independent of the angular momentum, but the wave function depends on the angular momentum values, let's say m, right?
yeah.
So it's kind of a similar way of understanding how degeneracy comes. Up to this point, there is no mention of fractional quantum Hall effect. uh, you cannot understand fractional quantum Hall effect. Once you consider Coulomb interaction potential, and then there is a kind of band gap creation within a single Landau level, disordered Broadbent, let's say Landau level, or Coulomb interaction Broadbent Landau level, then you start those discussion.
Okay. So, like
And
in
it happens to be that if you consider Coulomb interaction, then those wave functions are almost can be represented by those z to the power m, e to the power minus z square, and so on.
okay. Can I ask one small
Mm-hmm.
for
Sure.
so if I in general, if I want to understand like why one has to go to the symmetric gauge for fractional quantum Hall effect. So what should be the answer like this for?
Okay, so why one should go to the. No, I actually do not have any clear answer to this, actually, seriously. Of course, the superficial answer and the vague answer would be key. What Laughlin wrote, kind of it actually motivated from, let's say, symmetric gauge solution. But again, that's not a physics answer, right?
Yeah, yeah. Like the connection I wanted actually,
Hmm.
like why the symmetric gauge is important for this fractional quantum Hall effect.
Okay, I'll think about it actually, and I'll see that review if something is there in that review paper.
Okay, okay. Okay, and a few more thing actually regarding this discussion on this Kane-Milli model.
Okay.
When it was discussed in during the lectures. This Holden model was actually
So
mentioned.
Holden model, I plan to do a little bit today itself. So
Okay,
let's
okay,
go to other questions and then we can come back to this.
okay, okay, okay.
So another thing was Cramer's degeneracy, right? While calculating Cramer's degeneracy, how does I sigma y acting on UK? You mean just that wave function,
This blocks,
eigenstate,
blocks wave function
right?
I understand actually.
Uh-huh.
Apart from this e to the power I k dot r
Mm-hmm.
bar.
And that's okay.
Yeah, this sigma bar I can understand. This is because of the sigma y operator acting. So it will be like having some sort of this spin flip as we do for the sigma x operator.
Mm-hmm.
But why this minus k is coming actually? Like k is
Achha,
becoming minus k.
no, so you want the derivation or if you want to understand physically what is happening?
This anything is
So,
okay actually.
so physically, what do we mean by time reversal symmetry? Time reversal symmetry means when you say that a system is time reversal symmetric, then we can say that time reverse motion is kind of same as the time forwarded motion, right? Of course, we cannot go back to the time, but in the condensed matter case, we mean to say that let's say velocity. So velocity of some function, how it changes under time reversal symmetry, when we do k2 minus k. Under time reversal symmetry, k goes to minus k because k is kind of momentum, right? So if k goes to some other minus k prime under time reversal, or let's say simple k prime, then it is not time reversal symmetric. The system is not time reversal symmetric. So the main point of time reversal symmetry is that you should reverse the motion and see what is happening. That is the main point. So the definition itself includes that if I have to reverse the motion, then under time reversal symmetry, k should go to minus k because k is some kind of motion. So uh, if you simply think of h bar square k square by 2m epsilon h, then vk will be simply proportional to k, right? Del epsilon del k. So it's kind of k is representing the velocity, direction of motion. So if the
Yes.
direction has to change, then k has to go to minus k. That's one way of understanding it. And why sigma changes sign? Sigma goes to minus sigma or sigma bar also sometimes we call it, because again, spin has some intrinsic angular momentum, right? So if we think about simple angular momentum, not the intrinsic spin, let's say we have a particle moving around this direction, then we'll have some angular momentum along this direction, let's say out of plane. If we reverse the motion, then we'll have angular momentum along the into the plane minus L. So from this, we can say that angular momentum changes sign under time reversal symmetry. So if we reverse the motion of the particle, so it was going around this and around this, they have opposite angular momentum, so it changes sign. Similarly, spin also has some intrinsic angular momentum, so it should also change sign. S goes to minus s, it should happen. Of course, we should not understand spin in terms of this rotating particle and so on, but since it is angular momentum, spin represents, so basically s happens to be h bar by 2 sigma, where h bar has the unit of angular momentum, right? So from this we can understand that under time reversal also sigma should go to the sigma bar.
Okay. So basically, as you mean to say, is like the minus sign is due to this time reversal symmetry.
Right. And this I sigma y k is actually a time reversal operator.
Okay. Okay. Few questions regarding this time reversal
Hmm.
symmetry, just for understanding. Like uh, when we consider graphene,
Hmm.
they are actually that we try to break the time reversal symmetry in order to get this topological insulator
Right.
thing.
Hmm.
Is it
Hmm.
correct?
Yes.
And that's what we do by breaking the time reversal symmetry.
Right. Huh.
And but when we are actually going to this quantum spin Hall effect,
Mhm.
there, even though the time reversal symmetry is not broken, still
Mhm.
we are getting some kind of this topological the
Right,
spin Hall insulator behavior.
right, right.
Okay, okay,
No,
okay.
so the point is ki topology is not one type, right? So when you say topology, we
Yeah.
generally mean to say okay, Chern topology, but Chern topology is
Okay.
another thing, Z2 topology is another thing, and these are different aspects and different features there. So
Okay.
for example, Z2 topology is defined for time reversal symmetric system. So a point is ki if we only think about Chern topology or Chern insulator, then we can say that okay, if the system is time reversal symmetric, then there is no topology in the system because topological invariant, that is Chern number, is itself zero, right? But that's not correct.
Yeah.
That material can be uh, topological in other sense, which is quantum spin Hall effect. It cannot have
Okay.
edge current of charged particle, which is electrons. It can have spin current at the edge, right? So in
Yeah.
so
Yes.
there we define Z2 and other things, which is compatible with universal symmetry. So that's the point. So it is not really universal to say time reversal symmetry is needed to, I mean, broken system is topological or not.
Okay. If you have time today,
No, I have
like
time
if you
actually till 8.
okay, okay. So, like, actually, I didn't understand this Z2 topology properly. Like, I understood these chart numbers and how these topological invariants and all those things are coming. But this is some different kind of topology, as you also mentioned now.
Right, right.
So, uh, briefly, can you tell this Z2 topology, like,
So actually,
or
let's
if
defer
not today,
that. Let's defer Z2 topology for tomorrow. I mean so there is one extra session that is going to
yeah,
happen.
yeah.
I forgot the
Okay,
timing
okay,
actually. The
okay, okay.
day probably 18th September, but I am not sure ki it was from 10 or 6 itself. I have to see.
Okay,
So
okay.
did you get any mail for this? I have not received it.
No, no, I think.
Okay, so I have to see then.
Okay.
But then
Yeah,
I
yeah,
can
that is
prepare
also
some.
okay actually.
Right.
Yeah, yeah, sure, sure.
Okay, so any other question? Otherwise, I'll briefly mention that Haldane model actually.
Yeah, okay, sure.
Sir, I have one doubt.
Hmm.
Sir, how can we know that means theoretically, if I go, how can we know that the time reversal symmetry is broken or preserved in a given compound, sir?
Uh, so
Is
first
suppose
thing,
if we
hmm,
see,
first thing we
yeah,
observe or we just think about it, if it is ferromagnet or antiferromagnet, any magnetic order is there because magnetic order intrinsically breaks time reversal symmetry, right? Similar to the B goes to minus B. M is magnetic order or let's say magnetization, it also switches its sign. So if there is magnetically ordered material, there is no time reversal symmetry. Okay. Uh,
okay, sir.
Normal ferromagnets, antiferromagnets are like that. If it is not if it is non-magnetic material, then we can say that time reversal symmetry is preserved. So that's the first criteria to say about it.
Okay, sir.
Okay, so I'll just briefly mention Haldane model. Although there are a lot of details, I'll not go through each of them, but the main essence I'll try to convey. Okay, so let's start with graphene again. So graphene have this kind of honeycomb structure, let's say, right? And we have, I mean, these three nearest neighbor vectors. Their notations are a little bit different. A1, A2, and A3 are kind of nearest neighbors, and the unit cell is given by this one, okay, where it contains two kind of atoms, A and B. So basically we say this as a bipartite lattice, and if we derive the tight bending Hamiltonian, as in one of the tutorials we have already derived, if you see that the Brillouin zone is also hexagonal, okay, and at 6 distinct point you will see that conduction band and valence band exactly touches at each other. If you zoom out this portion, some k or k prime, you will see that there is almost a perfectly perfectly linear band dispersion along kx also, along ky also, okay. And in our Hamiltonian we didn't have anything more, I mean much, we just had this kind of term, let's say, write it. So Hamiltonian was simply 0 f k f of k prime, or the vice versa, that depends on how do we define fk. And fk was simply kind of, okay, so there might be some hopping parameter t, and I mean summation of e to the power I k I, sorry, to the power e to the power I k dot ai, let's say, according to this notation. And I mean ai corresponds to this nearest neighbor vectors, okay. Now so and t is the nearest neighbor hopping parameter, so this hopping parameter are, let's say, I mean determined by t, and we have no gap in the system, as well as massless Dirac fermions. H is represented by something like h bar vfk, where vf is proportional to t hopping parameter, and so on and so forth. Now now let's say we want to open a gap in the this band structure, let's say. It will be clear after a while that why we want to create gap and so on. But so this graphene, pristine graphene, is both time reversal and inversion symmetric, okay. So inversion symmetry you can easily understand from this from this figure itself, that let's say this is the Brillouin zone, and if you, this is, let's say, the midpoint, okay. So the red point is the midpoint, origin of this. Then environment, although the atoms are different, but then in terms of band dispersion and other things, these are equivalent environment. If you go to R2 minus R, they are essentially same, okay, in terms of band dispersion and so on. If you go to K2 minus K, the band dispersions are same. So these are inversion symmetric, and it is also can be shown that time reversal symmetric. And how can I show that it can be time reversal symmetric? So you just, sorry, so you have Hamiltonian like h bar vf k dot sigma, and you operate p h t inverse, let's say, and if you get h of minus k, and this was, let's say, h of k, then it will be time reversal symmetric, because under time reversal k goes to minus k. Now if we have Hamiltonian at k and minus k same, then we can say that under time reversal the Hamiltonian is symmetric, I mean TRS symmetric, and so is the my band dispersion and other things is going to be. And for this you can just simply apply I sigma y k. K is the complex conjugation operator, okay. CC, complex conjugation operator. So this you can easily show. Now let's say we want to break the time reverse, sorry, inversion symmetry. Time reversal symmetry breaking is another, we can break by magnetic field and other things as well. We will come to that. But let's say we want to break time reversal symmetry, or we want to have a system which breaks time reversal symmetry. Yeah, yeah. So this is HBN lattice, let's say, where we have, these are, let's say, H, and this is, let's say, PN, okay. or there are two different atoms, let's say. So these A atoms and B atoms are different in size, and also they are not carbon carbon as it was in the graphene system. So what really happens is that this kind of system which have identical structure similar to the graphene, but there are different atoms. Different means chemical composition itself is different. In graphene we had only carbon and carbon, right? Although they are inequivalent carbon, but that was not breaking inversion symmetry, let's say. But here we have different I mean atom altogether. Okay. So this HBN means hexagonal boron nitride, actually. B and N, these are, let's say. Okay. So these due to this different chemical composition, and also if you can see the band structure, they are gapped and they are parabolic. Actually here it is not really linear. If it would have been linear, this was the case, but now it is parabolic, right? So these are the parabolic bands. So this is the breaking of inversion symmetry. And how can you simply understand the breaking of inversion symmetry? If you have, let's say, Hamiltonian, something like, again I'll go f of k, f of star k, and f of k, let's say, now includes hopping term, let's say, and conventionally to the power I k dot ai, let's say. Ai is the nearest neighbor vectors, and this is in the basis of let's say, write it b and n atom, let's say, b and n atom, b and n atoms orbitals. Then if we give different on-site potential to this atom, so this atom is sitting at some potential and this atom is sitting some other potential. For easy to calculate, we I mean put it v and minus v, but that doesn't matter. If you put somewhere it is v1 and v2, these are different, and then f of k, f of star k, it will have the same effect. So basically inversion symmetry will be broken because the sublattice environment itself become different, actually. Okay. And this is intrinsic to the HBN. You don't need to apply any external electric field or any other thing. HBN structure is such that so these boron atoms, let's say, and these nitrogen atom feels different potential or different of diagonal energy they have already inbuilt, and this breaks inversion symmetry. So there is a gap opening, and so is also the low energy structure of this. Okay. So this is the gap opening by sublattice asymmetry. So this is important term, actually, sublattice asymmetry. So in similar to the graphene, these A and B atoms we call different sublattice. Okay. In graphene we had two carbon carbon, which we call CaCb. Both are carbon, but different sublattice. They belongs to different sublattice within a unit cell, let's say. And here HBN case, boron and nitrogen, let's say, belongs to different sublattice. And once we have different sublattice potential corresponding to each orbital, let's say, we will have inversion symmetry breaking and gapped out dispersion, let's say. Okay. Now there is another way to open up a gap in the graphene itself, okay, which is the Haldane model. And what Haldane did is that he took graphene system itself, but he assumed that we have a periodic local magnetic field. Okay, so this is important. Periodic local magnetic field such that total flux through a unit cell is 0. So we'll have some so this was actually a theoretical construct. Later it has been realized in some other systems, but so initially it was proposed as just a model, because if you think really, how do you create local magnetic field such that total flux through a unit cell is 0? But it is important because it gave us the first idea to develop topological insulator and understand all of those things, non-trivial topology itself. So so he considered that we have some kind of arrangement so that local magnetic field can be created, where this is, let's say, the unit cell, and the total flux has to be 0 throughout it. Okay, and these are the conventional terms which we call Fk. Okay, so now we have two hopping, so T1 is nearest neighbor N, and T2 is next nearest neighbor N. Okay, so this one means next. So he considered that next nearest neighbor hopping also, and so these are next nearest red. So these are, let's say, A atom, these are, let's say, B atom. So this can be one, this can be another, and this can be another hopping elements. And then another way to do it, if you start from, okay, so I am removing this because they have already written blue to be A and red to be B. So let's stick to that. So the main point is that there are different ways of nearest neighbor hopping, right? Sorry, next nearest neighbor hopping. It can happen to A and B to B. And depending on that, see that why, so this is important, that when you consider, so this is, let's say, A and B. Okay, so this is also A and B sublet is picture. So this corresponds to, let's say, A. Now apart from this e to the power I k bi term, bi are the next nearest neighbor. So these are the bi terms, which, whereas it was ai was something like this, all the nearest neighbor, just the I mean adjacent atoms. So associated with each e to the power I k bi term, there is an additional extra phase e to the power I phi and e to the power minus I phi, and these are the that local magnetic field effect. Okay, so if you add these two phase, I mean these terms are there, but if you really think that this is plus phi and this is minus phi, so they I mean kind of together make it 0. Again here also this is minus I phi and this is plus I phi, so again together it makes it 0. So we will have a local magnetic field, so that within a unit cell the total flux is 0, but you are associating a extra phase with along with the hopping terms. Okay, and this we sometimes call T2 e to the power I phi, which is complex hopping integral, let's say, hopping. Yeah, any questions?
Yeah, actually, I explicitly asked this question. I think
Mm-hmm.
this, like, why this hopping term is complex in case of this Halton model, but in while calculating this nearest neighbor term,
Mm-hmm.
and from there when we calculated this energy dispersion, there we didn't consider this I phi.
Okay,
So
so
here, like some underlying assumption is there,
the
like this you are giving
hmm.
some magnetic field, because of that and Arnold-Bohm effect, this I phi is coming.
Right. That's the way to understand. And another way is that if even if you include, let's say, if you include complex phase in the or to the nearest neighbor also, right? But the nearest
Yeah,
neighbor thing we can actually transfer to other sublattice. Let's say I have H psi equal to E psi, right? That's the main equation of energy. Let's say now psi is some component will be there, it is corresponding to A and B sublattice. Now here, let's say, if you add some phase, okay, e to the power I phi 1, let's say, you can actually transfer it to this element, right? And so you had H psi, which was simply let me just write it AB. Now you wrote it H prime and psi prime equal to E psi prime, and psi prime you just define, you take an extra phase of I phi 1 A and just B. So you just take some extra phase which was there in some sublattice. So the main point is you can transfer that extra phase for the nearest neighbor hopping to corresponding wave functions actually. So you can also generalize it to phi 2 also. Okay,
okay, okay.
but this if you just solve it, you can convince actually yourself, but just by once you start doing this kind of thing explicitly considering this diagonal terms also, you will not able to absorb those extra phase, these extra phases in the wave function, and then effectively we will write h bar h tilde is effectively h, the old h, and then we just have changed the psi tilde or psi prime, right? This is not possible for the off diagonal matrix, sorry, diagonal, which will come from the next nearest neighbor hopping. Why this will come in the diagonal term? Because next nearest neighbor hopping are happening with the same type of atoms, right? A or BB. Here this was happening
Yes.
AB, so that's why it was off diagonal. Now it is happening A to A and B to B, so that's why it is diagonal. So you will not be able to absorb those phases of diagonal terms. So that's one way to understand it. And of course, it was introduced by Halden, so with the mindset that okay, we will have local magnetic field, and due to Aharonov-Bohm effect, there will be some phase associated with each path, let's say. So that was the point.
Okay.
Okay, so once you have this Hamiltonian, you solve this, you see that we'll have band structure which is gapped. Okay, and these are the bulk band structure. What do we mean by bulk band structure? Bulk band structure essentially means that we impose periodicity condition. There is no open boundary condition. We have infinite uh, lattice system along x and along y, and in 3D case of course along z also, and we just have a well defined momenta along all direction kx, ky and so on. We just have the Hamiltonian and solve it. So these are called bulk state, bulk bands, bulk wave sets, or whatever. Now this is the band structure with second or next nearest neighbor hopping of 0.1 t1 and phi is pi by 2, let's say, some suitable phase, let's say. And we see the gap phase, right? Now the question is, what is really the difference between this gap phase of Haldane model, which we are able to get in graphene itself, right? And previously we have seen this was HBN, it should be small, so HBN. So in HBN also we observed that there are some kind of gap opening because the sublattice atoms are itself different. One is boron and one is nitride or nitrogen, let's say. So there also gap opening is there, and here also we have gap opening due to the Haldane model. Second nearest neighbor hopping, let's say. The question is, what is really the difference between the two? For this we need to study topology and finite geometric system. Finite geometry means now we are not in bulk, but we have, let's say, along x direction it is, let's say, infinite, and y direction it is finite. So something like no, opposite, let's say. So something like this, let's say. And of course these are uh, all other things are there. I mean, honeycomb structures are there. Yeah, questions?
So do you mean to say here, like when you consider this Holden model,
Hmm.
there uh, you will get this non-zero, non-vanishing Chern number by when you
Yes,
are seeing
yes,
this.
yes, yes. So, so non-vanishing Chern number for the for the bulk bands, right? What really Chern number
Yeah.
represents? It means that I have some non-trivial edge state, right?
Yeah.
Edges are conducting, but bulk will be insulating. Now, when you say bulk will be
Yes.
insulating, this is what we see already, right? If you have Fermi energy here, we are in the insulating zone. There is no state in between this region, right? So bulk is already insulating. So this is indicating that okay, we may have some non-trivial topology. Here also we can have non-trivial topology, HBN. And for that, what we usually do is that if it is feasible, let's say, we do finite geometry. We go to the finite geometry, not the bulk. We take some finite, let's say, along the x or along the y, according to our choice, and see what is really there. Is there any edge state or not? If there is any edge state, there is a one theorem called bulk boundary correspondence. Bulk boundary. So what it said is that in the bulk Churn insulators are basically insulating in the bulk, so they should not conduct electricity. But if you send electric field, you will get Hall effect, right? Hall signal. How do you get it? Because edge state conducts it. There are some state along the edge of the sample, because you are in the finite geometry, some kind of like this, and edges are conducting, and because of this, you will get uh, non-trivial topology and Hall effect and so on. Okay, and this is represented by bulk boundary correspondence. You are seeing bulk insulating, and that you are understanding in terms of kind of going to the finite geometry boundary states. Yeah. Yeah,
It
question.
just came actually. Yeah, it just came actually. This question, like, when you are considering this bulk and boundary is behaving differently,
They
then like boundary will be like conducting, but the bulk will behave as
right,
a
right.
insulator.
Hmm, hmm.
So then, how does one apply this Bloch's theorem for this case? Because
No,
in
no, no.
Bloch's theorem,
You
one
are trying to apply
uh,
Bloch's theorem for the finite geometry case.
yeah. So yeah,
No,
we
you cannot
cannot apply,
apply.
right?
Right, right.
Yeah, yeah.
Because
That's what
block
my
for
point
Bloch's theorem,
actually.
you need to have some periodicity,
Yeah,
well-defined
PBC is
momenta.
required
Right,
actually for that.
right. For x direction, in this case, you may apply. But then, how do you calculate Chern number? Because you need
Yes.
well-defined momenta. 2D integral you need to do, right? Ky is.
Yeah. Then how does one? Yeah, yeah.
So what we do is that we actually literally take finite geometry. Okay, and so why we write Hamiltonian 2 by 2, right? Because there is periodicity, right? Once we have unit cell, and you just repeat those unit cell infinitely, and you get the lattice. That's the main point of periodic boundary condition, let's say, right?
Yes.
Now
Yes.
in finite boundary, you just write Hamiltonian big matrix. I mean, it can be 100 by 100, 500 by 500, depending on how many atoms you get, because you are not able to represent the whole system by unit cell. So you have to go to the each atom and say what is the I mean, what is really the hopping and so on. So you include that. This is, let's say, 0, or since we are in Halden, so let me write T2 also, T2 something, T1 something, and you go on like this unless you finish your all the atoms. It depends on geometry you choose. You choose 100 atoms, you will have 100 by 100, let's say. You will have 200 atoms, 200 by 200 for graphene. Okay, and it goes on. So this you need to numerically solve and see what is really the band structure, what is really the wave function, and so on. Then if you see edge state, you'll say that okay, there might be non-trivial topology, or there is non-trivial topology. Okay.
Okay. Okay.
So I think this will be clear if I show you some. Of course, this is not my code. I'll just use some ready-made software. But again, this is very established and very nice. So let me share. Okay, we might go over time, but if you are fine, then so okay. So I'll just show you some graphene, I mean nano ribbon, which we call finite geometry, and how the band
Okay.
structure occurs. Okay, so I'm not sure it will uh, appear or not, but so you're seeing my screen, which is quantum lattice and so on, right?
Yes.
Okay. Uh, okay, so this is hopping Tij. This means that uh, normal T1 hopping in our case, okay? Just the A to B hopping,
Okay.
nearest neighbor. And there are other
Okay.
terms, don't need to give any importance of Rasba, exchange, K-meal, and so on. We are just interested in the Halden model, okay? Halden, I'm taking, let's say, uh, following, let's say, it's not exactly on, let's say, 0. Maybe 5. So this Halden term essentially means that next nearest neighbor hopping that we are just a while ago talking about. And we choose honeycomb zigzag. honeycomb zigzag means we are in the graphene system itself. So let's choose file just to understand, and let's see how this band structure. Sorry, this is the structure actually. Okay, along y
Okay.
direction it is infinite. Along x direction you see there are no atoms. So you have cut it, and zigzag you call because this structure is kind of zigzag. Okay, it will be clear not from this figure, but we just can Google it why it is called zigzag. You will understand that there is some cut in the zigzag direction itself. So it will be like tear up, something like this. Okay, so we
Okay.
choose this to be honeycomb zigzag, and let's see how the band structure looks like. So let me go. Yeah, see that, you see the bulk is still kind of insulating, right? The bands are not
Yeah.
touching, not semi-metal, but then there are two edge mode, or two counter propagating. Let's say one counter propagating along this and one counter propagating along this. So this have velocity, let's say negative, right? Del E del K, if you take negative it will be, because angle is more than 90 degree, and this is positive, right? So these are counter propagating edge state. This will reflect in experiments if you do uh, same, I mean edge state transport and so on. And if we change the geometry armchair, and interestingly there will appear no edge state, I think. Yeah, uh, so you see there is no kind of edge state. Of course they're touching uh, through the bulk or the bulk insulating edge. There is no counter propagating edge crossing each other, right? Similar to the
Yeah.
zigzag state. So this is considered to be the trivial state of armchair direction. So the structure we can see. So previously we have seen that it was cut along. If you see this is the cut along the y direction actually, and it is infinite along the y x direction. It's not clear because it is cutting. It's not going along this,
Okay.
but it will be clear. So if we change the, let's say 10, maybe it will show. Oh, sorry. Uh, nothing really happening. I just wanted to show another thing, that why it is non-trivial. Okay. It's not responding. So let me reshare. Just a second. Huh?
Yeah. Sure.
Okay. Still not respond. Yeah. Okay. So we have seen that if we have zigzag direction, nano ribbon, or finite geometry, graphene, uh, and if we add, okay, so what I was trying to tell is that if we have zigzag direction nano ribbon, and then if we add Haldane term, then we are observing that there are some edge state. But in the armchair direction, if we do the same thing, including Haldane term, which is next nearest neighbor hopping, there was no uh, edge state, right? This we then we can say that in the zigzag nanoribbon of graphene, if we add Haldane term, this is becoming topologically non-trivial. There is bulk boundary correspondence and so on, and otherwise it is not. Now, and of course, there was, we add only the sublattice imbalance. What do you mean by sublattice imbalance? I was showing that if we add this diagonal terms b and minus b, some constant potential, let's say, at two different atom, which was the case for HBN model, right? Diagonal terms were different, but then it was also gap. Now I want to see that is that gap trivial or non-trivial, which means that is there any edge state if we just add some constant potential at A sublattice, let's say V1, and B sublattice minus V1 or V2, then will I get topologically non-trivial state or edge state? And by adding sublattice imbalance, I am doing actually that. Okay, 0.5, let's say again we are in honeycomb zigzag. Again the structure is same. Now I want to see the bands. See, so you can see it, right? Hello.
Yes. Yes.
Yeah. So
Yeah.
so there are some kind of states connecting, but then it is not crossing the bulk, right? I mean the bulk band gap. So if it is not crossing the bulk band gap, if I have a Fermi energy somewhere here, then it is kind of same insulating state. I mean trivial insulating state. It will not conduct. It will not have some non-trivial topology. It is not a topological state. So gap opening, which we have seen in graphene, and gap opening is also possible in HBN due to sublattice imbalance, is not a different is not the same thing. It depends how you open the gap. You consider next nearest neighbor hopping, flux threading, or you just give some sublattice potential and want to see it is trivial or non-trivial. So that's the essence, and Haldane model corresponds to that next nearest neighbor case. I hope it
Okay.
was clear in case of yeah. So I was just trying to correlate with the bulk boundary correspondence and Haldane model. So if you have any
Yeah.
question, you can ask. Otherwise, we can close.
Yeah. Nice explanation. Thank you.
Yeah,
Thank you, sir.
yeah. So so if any other question is there, let me know in the mail at least 2 days before. Okay, otherwise it becomes difficult.
Yeah. Sure. Actually, I forgot.
Okay.
Otherwise, I would have sent.
Okay, no issue.
Maybe I will send you 2 days before. Actually, like
Okay,
maybe
okay.
on Monday or Tuesday, I will send
Mhm.
you.
Okay, okay,
Yeah.
okay. Thank you for
Thank you.
joining. I'm ending the.
Yeah.
Thank you, sir.